The last part of section 4.5 is the second derivative test. So we know how to use the first derivative test to confirm if we have a maximum or a minimum. But now that we understand the concept of concavity, we can use the second derivative test as well. And sometimes this can be faster than the first derivative test. But let me warn you, now that you have two tests, there's some possibility that you're going to mix up the definitions and the processes for each test. So make sure that you have them sorted out and you know which one is which. The second derivative test uses the second derivative. So you will still find the critical points the usual way, but this time to test these critical points, you're going to use the second derivative. If your second derivative is positive, then you're concave up, which gives you a minimum value. So if your curve looks like a bowl, then most likely the critical point is a minimum. And then if your second derivative is negative, then you have like a hill because you're concave down, which means you would have a maximum. Now, if your second derivative is 0, then this test is inconclusive. You would need to do further investigation to figure out if you are looking at a maximum or a minimum. Let's use the second derivative test to find the local extrema for the function f equals x to the fifth minus 5x cubed. So of course we're going to find our critical points the same way that we normally do. Take our first derivative, set it equal to 0, and solve. I'm going to factor out the common factors first. So I have 5 and x squared are common factors, leaving behind x squared minus 3. This tells me that x equals 0 is a solution, and then x squared minus 3 equals 0 is a solution, or x equals the positive or negative square root of 3. So we found our critical points. There's 3 of them. They happen at x equals 0, at x equals negative root 3, and at x equals positive root 3. Now in the first derivative test, we would pop these onto a number line, create the subintervals, and then look at the sign of the first derivative. But we're asked to use the second derivative test. So we're going to calculate our second derivative. If the first derivative looked like this, then the second derivative is going to look like 5 times 4x cubed minus 5 times 3 times 2x. In other words, 20x cubed minus 30x. This is our second derivative. We're going to plug each of our critical points into the second derivative to figure out the sign of the second derivative, to calculate concavity. So at x equals 0, our second derivative looks like 20 times 0 cubed minus 30 times 0. That is inconclusive. Our second derivative is already failing us. But we have 2 other critical points we can try. So let's look at negative cube root of 3. So we've got 20 times negative square root of 3, not cube root, minus 30 times negative square root of 3. And we only care if this is positive or negative. So we'll have the cube root of, the negative square root of 3 raised to the third power. That's going to stay negative. So we'll have, let's type that in on our calculator, 20 times negative square root of 3 raised to the third power gives us about negative 103.9. But then from that, we're going to subtract 30 times negative root 3, which is like adding 30 times root 3. Which does bring our number closer to a positive, but ultimately, type that into your calculator, you'll see that you get something like negative 51. So I'm going to put approximately negative 51, which means the second derivative is negative, concave down, which gives us a max. So we have a maximum at x equals negative root 3. And then we'll test our second derivative at positive root 3. So we'll get 20 times square root 3 cubed minus 30 times square root 3. Type that into our calculators. And we get positive 51 approximately, which means our second derivative is positive. We're looking at a minimum. We were able to use the second derivative test for 2 of our critical points, but let's revisit the inconclusive case. Because it's inconclusive, we have to work a little bit harder. We need to figure out if 0 is a critical point. Right now, we just have inconclusive. So we're going to revert back to our first derivative test and test around 0 using the first derivative. So I'll pick a point to the left of 0, like -1, and to the right of 0, +1. Plug that into our first derivative and see if we get positive or negative. So -1 plugged into our first derivative. Well, if we go back to our first derivative, notice that each of the variable terms have even exponents. So that -1 just turns into a +1. We have 5 minus 15, which is less than 0, so it's a decreasing function there. And when we plug +1 in, it's identical. We have 5 minus 15 again, which is still less than 0, so our function is decreasing again. So the second derivative test gave us back inconclusive, and this will always happen in the case of a kind of fake out critical point. This is not a max or a min at 0 because the function is decreasing on both sides of 0.